Alrighty, howdy folks. This would be the last chapter. There are quite a few sections in this one, so let's see how many of these we can get through with. But let's start with section 1, which is quite possibly going to be a fairly short one because I just want to cover a couple of ideas in this one. And as you can see from the title, it's about what are called vector fields. Vector fields are very important. And for example, those of you who are taking physics 2, you probably heard of charge field, electric charge field, right? And magnetic field, electric field, force field, all kinds of things are actually vector fields. And so we really need to get a grip on it. And it's a fairly understandable mathematical concept. So let's start with the definition of a vector field. Let D be a set in R2 as a plane region, R2 meaning the x-axis is a real number axis and the y-axis is also a real number axis, and you got points in that R2 plane. So basically any point can be represented as an ordered pair of two real numbers, right? That's basically a plane, the xy plane that we typically talk about, and that's R2. What do you mean R2? Is R is real? Are there things like C2 where C is complex? Yeah, in fact, there is such a thing called C2 where each axis is a complex axis, in the sense if you were to just imagine just a single line, there is no such thing as a single line, but a complex number. Well, anyway, A plus IB kind of a thing. So you could have something like that. A vector field on R2 is just nothing but a function f, but then notice you have to call it as a vector. Okay, a vector is a function f that assigns to each point xy in the domain a two-dimensional vector f of x comma y. Okay, if you take a certain point xy, at that point there is a vector. Okay, so I figured the best way to talk about this is actually go to GeoGebra and show you a few different scenarios of this one. Okay, the first thing I want to do, I called it as field around charge. This is something that you would have seen in physics 2, or you are about to see in physics 2. In physics 2, they say something like, all right, why do I have this grid on? Maybe I'll turn the grid off. Okay. Even the axis off. Cool. So if I do that, now let's say there's a fixed charge, and let's say it's positive. And then you try to bring another positive charge. You place a positive charge in its vicinity. Then because both the charges are positive, there would be a repulsive force, meaning this charge will try to push this away from itself. It won't let this guy come close to him, right? And so as you can see, what we're trying to look at is that force of repulsion at different xy points in this plane. If it's over here, what's the repulsive force? If it is over there, what's the repulsive force? Meaning force being a vector has to have both magnitude and a direction, with what force it is pushing it away and in what direction is this charge pushing this away, right? Those are the things. Now, as you can see, if we were to plot at different points these vectors that we are seeing, then we will in fact have a vector field. I have examples of that also, but here is what I wanted to show. And then something that you know is just like gravity. Newton's law of gravity says what? The force between two objects, two masses, m1 and m2 is F is equal to g m1 m2 over d square. So g is the gravitational constant, m1 and m2 are the masses of the two bodies, over d square. That's the key. And d is the distance between the two objects. So the force acting, the gravitational force between two masses is inversely proportional to the square of the distance. That means if the two bodies are close, then there is greater amount of gravitational force. If they are far away, boy, that force starts to become smaller and smaller, right? Because of the inversely proportional, and not only inversely proportional, but inversely proportional to the square of the distance. Cool. Charge is electrical repulsive force and attractive force are pretty much the same way. Q1, Q2, so this is some constant, and Q1, Q2 over d square. Q1 and Q2 are the two charges. Let's assume that they are the same. In this case, at least, they have the same positive charge. But what is essential is to understand that that force is inversely proportional to the distance square. So if I were to bring this closer, as you can see, that arrow is getting larger and larger. That is to indicate that this force is getting more and more repulsive. It's a larger repulsive force acting is the idea. And I don't know, will it allow me to bring, yep. See, if I make the distance 0, that's infinity. There is infinite amount of force acting on it. But then if you go just slightly far away, then it's at least become fairly finite, right? That's the idea. Okay, so far as vector field is concerned, we can actually draw different vectors. For instance, at this point, okay, if I were to, I wonder if I could have put a trace on this. Let me try that. Trace on. It's, oh, maybe I should draw the trace on for that also. Whoa, Nelly. See? Wow. Look at this. So that's basically a vector field. I'm able to show, oh, that is so cool. Man, I spent so much time trying to prepare for this, making all of this, and it never occurred to me to do this. Cool. So you have inspired me into something. What you are seeing here is kind of the vector field, because it's indicating, hey, at different x, y values, what would be the force as a vector, and force being a vector. That's the idea. Cool. All right. So should I save this? Nah, I won't. Let's move on to another scenario. Here, what did I call it? Field around a dipole. Ooh. Here, this is the scenario here. A is a negative charge, and at B, we have a positive charge. Cool. And C itself is a positive charge. Now what's going to happen? Well, this charge C is going to experience something interesting. This charge A, because they are in opposite, they have opposite polarity, charge A, by being negative, will try to pull this, will attract this positive charge. Whereas B, being positive, will repel this charge. Now, as a result, I think I do have it. Yeah, you see? So we have actually two components. At this charge is experiencing a repulsive force pushing it that way, whereas this negative charge is pulling it, is attracting, exerting, that's the word I was looking for, is exerting an attractive force on this charge. Cool. That's to be understood. Now, what in the world is this? This is just the resultant of the two vectors, meaning the actual force, electric force acting on this charge is this one, is in this direction, a combination of attractive and repulsive forces of the two. And again, at different points, the magnitude and the direction will change depending on which one it is closer to and all kinds of things like that. So we need vector field for this. And then I also have this. Okay. Now, I just saw that on Google, somebody, I did a Google search, and some wonderful person, bless his heart, had this program and made it into a nice thing with inputs. So all we need to do is input, if we want a vector field, there's an x component and a y component. X component of this force is F sub 1. The y component is F sub 2. So it allows us to enter what the x and y components of this vector field are. So here, let's say, I think in the book, the problem 12 says, okay, draw the vector field with y as the x component, yi plus the quantity x minus y j. Okay, and so all we need to do is just type these things. We can change this to, if you want, you can change y to y square, x minus y to whatever you want. And if you do, automatically the vector field is drawn for you. Okay, isn't it simple? My goodness, without this software, I don't know how people taught Calculus 3. And so that's probably why I never taught Cal 3, because I was like, man, I can visualize it, but how can I communicate to the students? But now that we have GeoGebra, I'm all excited about teaching Cal 3. Cool. What else can we do? And this guy gave this person, I don't know, why should I say guy? Could be a wonderful girl. So you could actually zoom and do things like that. Density, I like this density button. So it'll draw more. I think maybe that's the limit. I had to set a limit to it. Cool. So this is what a vector field looks like. It's kind of like what we did there, except that it picked a nice grid of points. You will understand the grid based on the tails of each of these arrows. So I think what this person did is pick like 0.5, 0.51, 1.52, 2.5, something like that. And for x and y, and then plotted at each of those things what the vectors would be. Okay, to me, this is all. I'll make this particular GeoGebra file available to you, so you can play with it. You can type whatever F1 and F2 components, the X and Y components of the vector field are, and play with it, and play with it in other ways as well, if whatever you want to do, Cool. And what else? I have done the same thing for another problem. Problem 14, where the x component is cosine of x plus y, and the y component is equal to x, right? And try to sit down and try to understand why does this make sense? The fact that these are the components means the vector should look like this. Does that make physical sense to you? You got to think about those things. What else? Well, those of you who would be taking some kind of a fluid mechanics course, you will bump into vector fields quite a bit, because imagine a flow of a fluid through a pipe or something like that. then at the different points on the inside the pipe, the fluid will have different speed, in fact different velocity. In the sense, direction also comes into play, not just the magnitude. For instance, there is something called boundary layer effect. If the fluid flow is what is called laminar flow, the best way to understand laminar flow is, if you were to open a tap, okay, if you don't make the flow rate really high, in the sense open it up really and so water is gushing out, no, don't do that. Let the flow rate be very gentle. Then you will see that there is a smoothness to the flow of water. Or kind of like if you're dropping honey, the honey flows out nicely and smoothly, right? So when the flow is smooth like that, that's laminar flow. Whereas if you open the tap up really high, then that's water is going to gush out, and that is the turbulent flow. Now, in case of laminar flow, what you will find is at the boundaries, the velocity is actually zero. At the walls of the pipe, the velocity of the fluid is zero and starts to increase with being maximum at the center of the pipe, or the axis of the pipe. And all those things, all those things meaning the way it is flowing, the way the fluid is flowing, can be represented using a vector field like this. And chemicals and civils and mechanicals, we would be figuring out a whole bunch of characteristics based on those fluid flow fields. Okay, so this is pretty important. And with that, let me go back to this. Yeah, there's one more concept I need to cover, which is what's called a gradient field. Gradient, you remember we actually talked about this earlier as well. If f is a scalar function of two variables, then its gradient is given by del f, right? That's del, or grad f, and that is nothing but, del f is nothing but partial f with respect to x, I, plus partial f with respect to y, j. Okay, what do we mean by del f? Del f means, like I said, partial f with respect to x, that's the x component. Partial f with respect to y is the y component of that the gradient vector. Now, what has that got to do with this? Take a look at this. Does that look like a vector field? What is a vector field? Oh, a vector field on R2 is a function f that assigns to each point. Isn't that what's happening? At each point xy, we have an x component and a y component. We have a vector with a certain x component and a certain y component. So basically, this gradient of f, del f, is in fact a vector field. That's the whole idea. And the components are partial f with respect to x and partial f with respect to y. Cool. That's another concept. I just got a problem here. Find the gradient vector field given that the function is y square e to the xy. Pretty silly, simple problem. All you need to do is figure out partial f with respect to x and partial f with respect to y. So basically, I took the partial derivative of y square e to the xy with respect to x first to get the x component. So y square is a constant, e to the xy. Differentiate that partially with respect to x. So you get e to the xy times the derivative of xy with respect to x would be just y. Right? Y is a constant. The derivative of x is 1. So you get that. Now, the y component, on the other hand, is just a tad involved. We need to apply the product rule, and that's what I'm doing. First function, y square, times the derivative of the second function is e to the xy times the derivative of xy is just x with respect to y, right? So x times x should be treated as a constant times the derivative of y is 1. That's why I have a times x here. Plus the second function, e to the xy times the derivative of the first function, y square is 2y. So that's what I have. Cool. That's it. So this is basically, of course, I simplified it. Y times y square is y cube, I said. And I factored out a y e to the xy and got this one. So you can do a problem like this, right? Find the gradient vector field of f of xy equals 1/2 of x minus y square and sketch it. Yeah, same idea. But the only thing is we have to go ahead and actually draw the vector field. And what I noticed was what we can see is it turns out to be x minus yi plus y minus xj. So I just went to GeoGebra, used that program, typed in x minus y, and then for the x component, and typed in y minus x for the y component, and it gave me this, took a snippet of that thing, and I posted it here. That's all there is to it. Cool. Guess what? We're done with this section.